All right, so let's do chapter 7 and 8 review. Okay. Okay, so what are the things that we covered for 7 and 8? We'll go through it quickly. Okay, so the first thing we started with was electric force. Okay, which was Fe, which equals to K Q1 Q2 over R squared. What does this basically mean? Well, if I have two charges, positive and a negative, there is a force of attraction or repulsion. So, anytime there is a force of any kind between charges, so force does not exist if an object is by itself, correct? Only if another object is there, then we can talk about force. So this is electric force. Q1, Q2, of course, are your charges. Charge 1 and charge 2. R is the radii between them. Okay? Now, we did a lot of questions here where we use vector components. So, of course, when you are doing questions, you need to make sure you keep in mind vector components, because that's what I asked you to solve for on the test as well as in the class. So this is what we started with. Okay? The next thing that we did after this was electric fields. Now, electric field is denoted by this variable. This is known as epsilon. Okay, and this is the area in which the force exists. The area in which the force exists. So we did Fe over Q, or we also wrote it down as K Q1 over R squared. And epsilon, of course, does not have its own units. Force has a unit. This is newtons. Okay, this is newtons per coulomb. This is newtons per coulomb. This is the area around a charge in which the force exists. Okay, again, we're also going to be using vector components for this. So please make sure you're aware of how we talk about it. And we said electric field comes out of the positive and goes into the negative. Okay, and for electric forces, we talked about if I have two charges, positive charge and a positive charge, then, for example, this is A, this is B. If I'm looking at the force on B, it will be a force of repulsion, so it would be FEAB, going to the right, because it is a force of repulsion. Okay, so that was what we talked about. So there was electric fields, number 2. Okay, the next thing that we talked about after that was electric potential. Energy. Electric potential energy, that's EE, which equals to K Q1 Q2 over R, measured in joules. Okay, now this was looked at in the same way as in chapter 6 when we talked about energy for an object in the potential well. So we look at electric energy in exactly the same way as well, because they are all related: electricity, magnetism, and gravity, in terms of their behavior, measured in joules. Okay. Okay. The next thing that we did after electric fields was electric potential. So electric potential, okay, also known as voltage. Okay, and we said electric potential denoted by the variable V, which equals to K Q1 over R. And we said this was the energy required, or the work required, to take or carry a charge from outside of the field into the inside of the field. So imagine there is a charge here already, and we're taking another charge that's far away, and we're bringing it from one point to another into a field. So this would be voltage or volts, measured in volts. Okay. We also talked about electric potential difference. And electric potential difference okay, again, this is delta V. Okay, and the best way to look at it would be I have a charge with an electric field. I'm taking a charge and moving from one point in the field to another point in the field. Okay, and delta V is epsilon times R, for example. Okay, so this is your electric field. This is your radius. Okay, are we good with this? So far so good? Okay. All right, so the next thing that we talked about after this was the concept of parallel plates. And here we talked about Millikan's oil drop experiment. Okay, and Millikan's oil drop experiment was basically you had a parallel plate, okay, with a charge on the top and a charge on the bottom. So imagine if I have a negative charge on the top and a positive charge at the bottom. Okay, and if my charge was a positive charge right here, of course you'll have Fg, which is pulling it down, and Fe, which is pulling it upward. Okay, and you can come up with a formula. So Fe, which equals to Fg, which is Q epsilon, which equals to M times G. Okay, and your Q can come out to mg divided by epsilon. And now we know epsilon equals to delta V divided by R. So we can say, since this is a parallel plate, there is an electric field going from the positive to negative like so inside the parallel plate. Okay, then we can say this can be written down as mgr divided by delta VB. Okay, now if I want to look at how many electrons there are in a charge, that's Q equals to N times E. We already know the charge of E. E equals to, of course, 1.6 times 10 to the negative 19 coulombs. Correct? Okay, we good with this? The next thing that we took a look at was energy of charged particles. Okay, and for energy of charged particles, okay, basically we're taking the old adage from before, E total before equals to E total after. Okay, and imagine if my object had the following energy, then it would be EE prime plus EK prime. Okay. So if I bring this over to the other side, this becomes EE minus EE prime, which equals to EK prime minus EK. And you end up with negative EK, which equals to, or negative EE, I should say, which equals to change in EK. Okay, EE can also be written down as Q times delta V, and this would be half mv squared. But remember, this is change. This is change. Change in energy. Okay, we also talked about lots and lots of applications of charged particles, of parallel plates in real life. So please make sure you're aware of that, you read up on that, and so on and so forth. Okay, so I will finish this video with just Chapter 7 review, and then we'll do Chapter 8 review in the next video. Thank you.